Good morning, friends. I welcome you all for my course, Engineering Thermodynamics. This course is to understand how a system behaves with the surrounding and how heat, work, energy, these things are transferred from one part to the another part. In my previous class, I have discussed about heat and the work. So we should understand that work is done whenever the system boundary moves. I have discussed in my previous class that if this is the system and this is here, we have the system boundary, this dotted line, this is the system boundary and this is the system, this is the surrounding and this is the boundary. If this boundary moves, then only work will be done. And also there should be a resistance force. There is a difference between work and the thermodynamic work. In a simple work, we say that work is equal to force into dot product of displacement. But for the thermodynamic work, W is equal to F resistance. This is very much resistance into dx. So here S resistance is required, but normally this is a force applied. So if there is no resistance, there will not be any thermodynamic work. To have the thermodynamic work, a resistance is required. I will give an example of free expansion. This is a chamber and here is a membrane and here is some system is there, gas with a high pressure, and here we have the vacuum. If we hear the vacuum and if you puncture this from here, it will expand here, but no work. No work in free expansion as there is no resistance. So if no resistance, no work. That we have to ensure and that we have to take care of, that some resistance should be there. So in thermodynamic work, we should be very much cautious that if there is no resistance, no work. So if it is free expansion or if you are moving in a vacuum, there is no friction and all, that time also there will not be any work. So in today's class, I will give some, these are the contents for this class: introduction of work, example problem 1, example problem 2, and then we will have a numerical problem, and then I will end this class. So we have to, in our thermodynamics, if you apply direct equations or the formulations in your real application, your result may not be correct. We should understand the concept and how the process is going. We have also discussed that the work and heat both are depend upon the path. They are path function. These are path function and their differential is inexact. So we write del W or del Q, not dW or dQ. because this is exact differential and this is only used for the property, and these properties are depend upon the points. But dw, delta W and delta Q, the work and heat, they are not the point function, they are the path function. So if I draw here, what is the difference between a point function and the path function? So you can see that if 1 and this is the 2, 1 and 2, so path may go like this, it may go like this, it may go like this, it may go like this, but both are reaching to the 1 to 2. So how this can be there? So if you see, this is the volume V2 and this is the V1, and from here this is the P2 and this is the P1. So we know that work done is equal to P dV, or P1 minus P2 on V2 minus V1. Okay, so P2 minus P1 and V2 minus V1. So this is the work done. But if you see here, the work done is dependent upon, if it is going by this, if you see here, I will put some other color. If it is going from here to here, the work done is the area under this. So area under this is the area under this. This is the work done for this process. And but if it is going, if I am writing A, B and C, if it is going 1A and 2, then this process may be like this. So it will, the area of this thing is from here to here, this area. So it is more than this. So it is depend upon the process, and accordingly the heat and the work both are not depend upon the point, but they are totally how this is going, how the process is moving and how they are getting. So that is the difference, and we have to take care of during solving the problem. We should not just directly use the formula. Formula may not work or may work. Okay, but if you go step by step, drawing the processes, then only we can solve the problem. This we will be showing in our examples and all. So objective of the today's class is define the concept of work, including electrical work and several forms of mechanical work, application of work on problem solving. So these are application of, okay, this is the application of work. So this we will be seeing. So work is what? I have just now explained. In work, it has to move against the resistance, then only work will be there. And I have shown if it is the free expansion, there will not be any work. So it is a mechanical work. We can also have the electrical work. So if you see the electrical work is depend upon the electromotive force and the charge into charge. So how much charge you are displacing with the help of the electromotive force, that is called the work. If you see the magnetic work is also there. So if you apply some magnetic force on a ions, and ions are moving here and there very randomly, and if you apply the one magnetic force north and the south, this all will try to change their position. They are random. Now they may be in a straight line, and so here this magnetic work is produced by using the magnetic field. So like this also there can be electrical work, magnetic work, and some other type of work are also there, like stretching work, or stretching work. If you have the wire and you are putting a force like this from here to here, it will try to expand. So the surface tension here, surface tension will be generated, and this will be generating the work. So next I am going for some problems, and you can see that in these problems very simple and basic things I will be describing, and the numerical problem will give you the exact explanation of the work and how we can go ahead step by step. I am going to explain. So here I am just giving a simple problem and how we can go ahead. A candle is burning in a well insulated room, taking the room, the air plus the candle as a system. Determine if there is any heat transfer during this burning process and if there is any change in internal energy of the system. So we know that the heat is a transient energy, and the energy which is stored in a system is called the internal energy. Heat and work both are the transient phenomena of energy. We cannot say that if the bucket of water is kept, you cannot say that this is containing the energy or heat energy. It is not having the heat, it is not having the work. If it is boiled water in a bucket, you cannot say that it is a heat energy. It is an internal energy in the water which is giving the heat. So we have to understand this concept. So here we can see that how we can go here. So here a diagram is shown here, and in this you can see that there is a room here, and this room is insulated by this red line. Here is a candle. This candle is illuminating and everything is insulated. Heat will not go out, or from out it will not go inside. So this is the surrounding here. This is the surrounding, and this is the system here. So inside this system, what is happening, that we have to see that. So here we can see a candle burning in a well insulated room is considered. So here is a candle. This is the candle here, and this is a well insulated room is here. It is to be determined whether there is any heat transfer and any change in internal energy. So we have to see that there is any change in internal energy or there is any change in heat transfer is happening or not. So we can do the analysis in this way. The interior surface is the system boundary. Here the dash line it is shown here. This is the system boundary. Heat is recognized as it crosses the boundary. I have just now told that heat is not inside. If it is able to cross, or then only it is heat. It is going out or the coming in, then only this is the Q. Same way, work also, either it has to go out, it is a positive, and if it is going in, it is a negative. Here, this is the positive and going out is negative. Okay, so this we have discussed. So the interior surface is the system boundary. It is given by the dash line here. In the figure, heat is recognized as it crosses the boundary. So if any from the system is going out or coming in, any heat, then we can say that it is a heat energy. Since the room is insulated, it is given here that room is insulated, the adiabatic system, and no heat passes through the boundary. So either it is insulated, heat will not go inside or heat will not come from the inside. Candle is burning inside, but heat will not go outside as the system is insulated and it is an adiabatic process. In adiabatic process, neither heat will go inside nor heat will go outside. It is inside packed, the system. So there is no heat transfer and heat. So here, heat transfer is equal to 0, means no heat transfer. No heat transfer takes place. Okay, because it is insulated and it is an adiabatic process. Second thing, we have to see that the internal energy involves energies that exist in various forms. So what is the internal energy? Internal energy, the heat exists in the various form. energy. So here it may be the sensible heat, it may be the latent heat, it may be the chemical heat, it may be the nuclear heat. So this type of heat is called the internal energy. During the process, part of the chemical energy, you see here, candle has got some material and this material is illuminating, burning, and this material is made of some chemical components, and this chemical component is converting to a sensible energy. Since there is no increase or decrease in the total energy, internal energy of the system, so U is equal to 0. So here it is giving heat, but inside all are same, because it is part of the candle is a part of system. So it is inside, it is burning. So internal energy, total internal energy will be also same. So there is no heat transfer and there is no increase or decrease in the internal energy. So discussion, there is a heat transfer from the candle flame to the air, but not across the system boundary. So because it is insulated, so it is not going out. So there is no heat transfer, there is no change in internal energy, because every energy is in the sealed pack, it is not going outside. So internal energy also 0 and the heat transfer is also 0. So this is a simple solution for the problem number 1. Hope you have understood that in this type of scenario, you won't get any heat transfer if it is adiabatic or insulated, 100% insulated system. You cannot get heat transfer, you cannot get your energy change. Now I will go for the same way. I will go for the example number 2, and let's see what is happening in this. Heating of a potato in an oven. So this is our problem, and this we can see that how the, so here a potato initially at room temperature, that is 25 degrees centigrade, is being baked in an oven that is maintained at 200 degrees centigrade as shown in figure. Is there any heat transfer during this baking process? So what is the question is, and what is the problem is, a potato initially at a room temperature 25 degrees centigrade is being baked in an oven that is maintained at 200, means the temperature of the oven is 200 degrees centigrade, and we have put the potato inside the oven. Is there any heat transfer during this baking process? So this we have to see that how we can go about potato being baked in oven, any heat transfer happen or not. This is our problem. We have to see that is there any heat transfer is taking place between the potato and the surrounding and the system. Analysis we can do that. Problem is not well defined as it didn't say about the system. In this, it is not telling that which is the system. Potato is the system, or the oven is the system, or the total is the system. So it is not well defined. That first we have to see that what is the exact system. If we see as a potato as a system, then there will be a different issue. And if we see that oven with potato, it will be a different system. Assume potato as a system. So first we are seeing that potato is only the system. Potato skin is as a boundary of the system. Part of the oven energy pass to potato by crossing the boundary. Since oven is at higher temperature, this will allow energy transfer from oven to the potato. This happens due to temperature gradient, and hence this is a heat transfer process. So this is a heat transfer process. I will explain with the diagram also. The oven air itself must be heated somehow. The oven air itself must be heated somehow. So this you can see here, that here is a insulated chamber. We can see that oven is an insulated chamber where heat is not going out or not coming in. We are putting the electric current. So oven is heated and the oven temperature is 200 degrees centigrade and potato is at 25 degrees centigrade. So this is the boundary. This you can see that this is the skin of this potato is the boundary, and it is kept, and there is a lot of temperature difference between oven and this thing. There is a heat will go from oven to the potato. So this is a real case. Due to the gradient of the temperature from high temperature to low temperature, the temperature of the potato will also increase and potato will be baked. So there is a clear indication that there is a heat transfer between oven and potato, and the direction of the heat transfer is from oven to the potato, as the temperature of the oven is higher than the potato. So this oven will give a heat transfer. But if you see, if you consider this is as a system, then the condition will be different. If you assume that this is the whole system, inside the system you have the oven, and there inside you have the potato, then there is no heat transfer from the system to the surrounding. No heat transfer, as it is insulated. No heat transfer takes place. So it is adiabatic process. Okay, so this is the second example which I have given here, and hope you have understood that how the heat is transferred. In the same, the system matters which you choose as a system. So system boundary should move. So in this case, if you see, if it is oven, heat will not move because oven is a insulated. So no heat transfer. So this is the second example, and I will go for the next example that may be numerical, and this we can see here the numerical problem. So a piston cylinder arrangement shown in the figure initially contain air at 150 kilopascal and 400 degrees centigrade. The setup is allowed to cool to the ambient temperature of 20 degrees centigrade. Estimate A is the piston resting on the stop in the final state. What is the final pressure in the cylinder? So, first question, the piston cylinder arrangement. As shown, this is your cylinder, and this is the piston, and this is a very typical example for any thermodynamic process. We take like this, and it gives our requirement. Most of the time we take piston and cylinder, and this can be applied to anywhere. So here there is a piston, there is a cylinder. So initially contains air, so inside we have the air, and this has the air at 150 kilopascal and temperature is 400 degrees centigrade. So this is our first condition. The setup is allowed to cool, means heat is going out. Heat out. So you know that heat out is negative. So it is cool to ambient temperature, that is 20 degrees centigrade. So the second case, it is 20 degrees centigrade, means from 400 degrees centigrade we have reached to the 20 degrees centigrade. Then we have to estimate, is the piston resting on the stop. So we have to see that at this condition whether this piston is reaching here or not. That is our first problem is the piston resting on the stop in the final state. So this is your final state, whether it is resting on this stop or not. And if it is resting, what is the pressure P2 on this, on the cylinder. So inside the cylinder here, what is the P2 in this condition? Then if you know this P2, then what is the specific work done by the air during the process? So how much work is done by the system in this process. So here I have shown the piston and cylinder arrangement. I have taken from this single book. This is the reference one, and this I have answers are here, and we will see that whether we are able to get these answers or not. So hope the problem is clear. So we have to go for the solution, and the solution is very, very interesting, and this is a real practical problem. If any cylinder is there and it is filled with the air and with some temperature and the pressure, and you have left in the atmosphere and it is cooling down to the atmosphere, 20 degrees centigrade is atmosphere. So after this, whether this piston will fall and how much it will fall, that we have to see in our problem. So here the given data are at the state 1. When this is the state 1, the P1 is equal to 150 kilopascal and temperature is 400 degrees centigrade. We can write it in the Kelvin, because all our ideal gas equations are derived with the help of the taking temperature as the Kelvin. So 270 plus 400, 670. I have not taken 273.15. I have eliminated this. Okay, so only I have put the 273 plus 400. It is a 673 Kelvin. So this is our initial temperature. Now we have to see the state 2. State 2 is given that temperature is falling to 20 degrees centigrade. So this 20 degrees centigrade plus 273. So it will be 293 Kelvin. First we should try to address the problem A, that is it hitting the stop or not. So first we should see that this cylinder from here, whether it is coming here or not. So that we have to address, and after if it is coming here, then we have to find out what is the pressure. So if it is coming down, so how much you can see area is constant. So it is initially 1 plus 1, the volume is 2, and as when it is coming here, the volume is only 1. So this parameter is changing here. So we should see what type of substance in system is. So we have seen that here it is given air. If in place of we get the water, then we have to use the steam tables. But here it is air, and that is air at a low pressure and a high temperature. If any substance is at low pressure and a high temperature, that we can assume as an ideal gas. So first we have to see that whether we can follow the ideal gas equation or not. In this case, it is air, and air is also at a very low temperature, very low pressure, nearly 1.5 atmosphere, and the temperature is very, very high. So we can assume that it is an ideal gas. However, in the real sense, there is no ideal gas existing. But for our simplification, we can assume that this air is an ideal gas. So here we can have phase changing substances like water, refrigerant, or some other things. If it is water or some other refrigerant, then we cannot use as an ideal gas equation, because they are not in this, they are in the phase changing, means from liquid to gas, gas to liquid, this will change. But air in this condition, mostly we can assume that it is an ideal gas. So we can idealize these gases. A real gas can be assumed the ideal gas at high temperature and the low pressure. As I have explained, it is a low pressure here, and this is the high temperature. So if any gases which are low pressure and the high temperature, we can assume that we can treat air as a gas in this given temperature and pressure, as temperature is high and the pressure is low. So T1 is 673 and P1 is 150 kilopascal, which is nearly atmospheric pressure. So we can assume this as a ideal gas. So treating air as an ideal gas is not a bad assumption. So air we can take as a ideal gas. Now we have to find whether it hit the stop or not. The second, we have to see that whether it is able to hit the stop or not. So now we have to find whether it hit the stop or not. So let us assume it hits the stop. So first assumption is it is hitting the stop. If it hits the stop, the height of the piston will have to move by 1 meter below. That is 2 meter to 1 meter low. So this I can draw here again. Initially it is here. This is your piston, and from here to here, this is 1 meter, this is 1 meter, okay, and there is a stop here. So this is the, so first the system I will just show here. So this is the system here. Okay, this is the system. Okay, and here is the air. This is the air is the system. So for the heating of this, it has to move from here. This point has to move and it is come to here, and then here I am just again drawing new position. It has come from here to here. It is hitting means here. So means the volume up to here is 2 meter cube, the height, and here is only 1 meter. Okay, so area is same. So this volume is directly dependent upon the height. Okay, so here we can see that at this case the V2 is equal to V1 by 2. I think you all will agree by that. So here we can see that this piston has to move from 2 meter to 1 meter below. We can say that here V2 is equal to V1 by 2. So that we have got from this idea that if it is moving by 1 meter, then it will hit this stop. For ideal gas, because it is air, just now we have discussed that we can take the ideal gas equation for air if air is in low pressure and high temperature. Here it is high temperature and the low pressure. Very well we can take this assumption and we can use. But if it is another substance like water, refrigerant, we cannot use this ideal gas equation. So here P1 V1 by T1 is equal to P2 V2 by T2. Here we should make sure that T1 and T2 to be taken only in absolute temperature, that is in Kelvin K. We should not use degree centigrade. We have to make sure that we know that the P1, T1 and V1 and V2 is equal to V1 by V2. We know that. So if we put this value P1, you know the P1 is 150 into V1 divided by T1 is equal to 673 is equal to P2 we have to find out, and this V2 is equal to V1 by 2 divided by 293. So from here this V1 is cancelled. So we can get the P2 is equal to 150 into 293 divided by 673, and this will also added here. So we will get here this answer as 130.7 kilopascal. This is the answer which is A part answer we got. So here the pressure is 130.7 kilopascal. This we got the pressure at this point. So we know that as the P2 we got 130.7 kilopascal is less than the P1 150 kilopascal. So it will hit the stop. So if you can see here initially how much it is given. This pressure is 150 kilopascal. So if it is the same, it will not move. So if it is hitting, then only the pressure will be dropping. So in this condition, the P2 is equal to 137.30.7 kilopascal. So 100% it will hit the stop. So that we can get that as the initial pressure will only change after hitting the stop. Because if it is not hitting, slowly it will move. But the pressure will be same till the time this is your stop. These are the two stop and this is your cylinder here. Understand, it is very good to understand this. This piston will only up to just before the touching somewhere here. Same pressure 150 kPa will be there. As and when it is just hit, the pressure will drop to 130.7. This indicates that it is hit. Till the time this pressure is not falling down, it is not hitting. That is the indication that all of a sudden the pressure is fall, and this falling in the pressure will indicate that the piston is hitting on the cylinder. So we are now sure that piston has hit the system and the pressure at that is 130.7 kilopascal. So part A we have done it. Now I will go for the part B and how to find out the specific work done during the process. So what is the specific work done? Means work done per unit mass. So work done per unit mass is called specific work done. So that is the first thing. So it is very much essential to draw the PV diagram to find work done. So we have to see that how to draw the PV diagram. Okay, so we know that work done that is from 1 to 2, work done from 1 to 2 is equal to integration from 1 to 2 P dV. So to get this, we have to draw PV diagram, because then only we can find the correct answer. We know the state 1 is given. State 1 is given. State 1, that is P1 V1 is given. So I will draw here. This is the P and this is the V. So state 1 is given here. This is the 1. We have to very much careful about this drawing. So I will draw here the piston again here. So just I will draw here again. This is the V and this is the P. This is the point 1. So in point 1, first thing I have to see that this is here piston, this is here stop, and from here to here is 1 meter, from here to here is also 1 meter, from here to here is 1 meter. This we can see here. I will okay, so we have seen here that this is the air, and here P1, V1, state 1 is given. State 1, that is the 150 into V1. Okay, so you see here that we have seen that the till the time this piston is not reaching up to here, the pressure will be same. Means from here to here, pressure is constant. This is the 2A. Means till this time from here to here, it is not touching, just above. It is constant pressure process. 1 to 2A is constant pressure. And up to here, the pressure is given as 150 kilopascal. So this is the 150 kPa. As it is hitting, and you are removing the heat, after removing the heat, you will see that it is a constant volume process. This is the 2. So this 2, P2 is given as 130.7 kPa. So this is the 130.7 kPa. And this V2 is equal to V1 by 2. So this is your V1 and this is your V2. So this V2 is equal to V1 by 2 as per the given condition. So this is your PV diagram. If you see in our high schools or intermediate, if these two conditions are known, so you can draw like this. This is not correct, because the work done between this and this is different than the 1, 2A and 2. So be very careful. Don't just follow the formula and you put the value, you will get the result, but that result is wrong. We have to first draw the PV diagram, and accordingly we have to follow the system. So we know that the work done is equal to, this is the dW, this is equal to 1 to 2 P dV. This we can write that 1 to 2A P dV plus 2A to 2 P dV. So here this we can see from 2A to 2, the volume is constant. So this dV is equal to 0. So this part is 0. So now this work done 1 to 2A P, it is P1, not P2. Okay, so this we can see here, it is P2 V2A minus V1. Okay, so here we can write here 1 to 2A P1. So V2A minus, so we can write it as a P1 V1 minus 1 by 2. Okay. Because it is given V2 is equal to V1 by 2. So here we can write V1 by 2. So V1 we have taken out. So here you will get half minus 1. So you will get minus 1 by 2. So here 1 by 2. So you will get here that it is not required. So you will, this we can do here, the minus PV is equal to MR T1 by 2 minus MR T1 by 2. So we know the T1 is given. So here for the 1 kg minus 1, because it is per kg, R is 0.278 and T1 is 673 divided by 2. So you will get the work done is equal to minus 96.6 kilojoule per kg. So this is a specific work done, because for per unit mass, here M is equal to 1. We have, because per unit mass. So in this way, we can see that this is the, so here we got the work done specific we have got here specific work done is equal to minus 96.6 kilojoule per kg. So what does it indicate? The analysis is what? If you see here that this is the piston, what we have seen here, and we are taking heat Q out. So it is cooling down. So the piston is moving from top to the bottom. Here, new position. This is the 1 and this is the 2. So this volume is reduced. So if any piston where the volume is reducing, so work is done from the outside. Outside work is done, and that is the negative. So if this is the system and work is going in, work in is negative and work out is positive. So here this minus indicate that this system, the work is coming from outside, so that it is pressing from here and slowly work is in negative direction. So that is the indication that our system is not producing the work, but it is obtaining from surrounding. Work is given from the surrounding. That is why this work is negative. So this is my reference which I have taken from Eunice Sengel, Michael A. Ball's Thermodynamics and Engineering Approach, Tata McGraw-Hill's. Also, I have taken this concept from concepts of thermodynamics by Professor Suman IIT Kharagpur. This I have taken from NPTEL lecture. NPT. So something I have taken from there, something I have taken from here. And thank you very much. Any questions, you are welcome to ask to this email. This is my email. And thank you very much for joining the class. Please be tuned in my next class also. In my next class, I will take few numerical problems. Few numerical problem on work and heat. Be tuned. Please like and subscribe my channel. Thank you very much for joining. Meet you soon. Till then, goodbye. See you. Jai Hind.
Like, share and subscribe. Hit the bell icon for more updates.